This is another question from AP Physics, from College Board, from AP Physics study guides. And I have a link or problem for you under FRQs for quizzes. So the problem states a cylinder with a movable piston contains a sample of ideal gas. A temperature probe and a pressure probe are inserted into the cylinder as shown on the right. The sample of gas is taken through a 3-step cycle A, B, C, and then back to A. The process AB, the volume is decreased to 1/4 its original volume, while constant pressure maintained. In process BC, the gas expands back to its original volume isothermally. And in process CA, the gas returns to its original state without any work being done on or by the gas. So for part A, they say on the axis on your right, draw a graph of pressure as a function of volume V for the 3-step process ABCA. Label states B and C. The pressure and volume of state A are PA and VA for the volume, respectively. Label the axis with the values of pressure for volume for states B and C in terms of PA and VA. So they tell me that the process AB, the volume is decreased to 1/4 of its original. So if I start from A, and there's 1, 2, 3, 4 divisions to get to VA, then it's going to decrease to VA at the constant pressure. So I know it's going to be this part. So this will be B, and going in this direction. Then in the process BC, the gas expands back to its original volume isothermally. So it's going to go back to its original volume isothermally. And I want to work this out with you. Let me do it here. So let's say we have this condition. It's an isothermal process. So I have PA, or let's do PB. VB is equal to PC VC. It's over T, but isothermal process tells me that T is still the same, so I'm gonna cancel this part. Then I also know that VC is the same volume as VA, which is 4 times VB. So I have PC 4 times VB. So if I look at this right here, PB, VB is equal to PC 4 VB. VB and VB cancels, and I see that my PC is 1/4 of PB. So I need to go 1/4 PB, which is right here. And it's isothermal, so it's going to look like this. So it's this process. And then the last one, CA, the gas returns to its original state without any work being done on or by the gas. And if there's no work done on or by the gas, it's isovolumetric. Volume stays the same. And this is going to be your final process. So you have B, and this is C, and then back to A. For the second part of A, they ask you for process BC, is the energy added to the gas by heating or removing from the gas by cooling? Support your claim using physics principles. So we'll look at the BC where the temperature is staying the same. So for the first law of thermodynamics, for the work energy theorem, so we have the internal energy of the gas, internal energy of the gas is equal to the heat taken out or added plus or minus the work done on the gas or by the gas. Because the temperature doesn't change, so internal energy of the gas does not change. Temperature stays the same, so internal energy stays the same. Then because the gas is expanding, so the negative work is done on the gas, or the negative work done by the gas, and positive work done on the environment. So for that reason, you have to have Q added into the system. So for the answer, you would say, for the process BC, is the energy added to the gas by heating or removed from the gas by cooling? So you would say the energy needs to be added into the system by heating it up. For B part, they say for process CA, is the net flow of energy into the gas or out of the gas? Explain your reasoning using physics principles. Describe one method by which this flow of energy could be accomplished in the lab. So if you look at CA, so here is our CA, you see that the pressure is increasing between C and A, but the volume is not changing. So if the volume is not changing and the pressure is increasing, the only way to do that is by adding energy into the system, by adding heat into the system. So for the answer for B, for the process CA, is the net flow of energy into the gas or out of the gas? So the answer would be into the gas. And when they say describe a method in which this would be possible, so you could fix the piston of the gas at a certain position. So you would fix the piston at a certain position and not let it move. And you can add the heat into the gas different ways. It can be a hot bath, or it can be flame, but any different ways you could add energy or heat into the system, and the pressure is going to increase when the volume stays the same. For C part, they say curves 1 and 2 on the graph show the distributions of particle speeds when the sample of gas is in 2 of the states. With curve 1, a state that occurs before curve 2 as the gas goes through the cycle. Which state corresponds to curve 1 and 2? Support your claim using physics principles. So at first, before I start thinking about what is happening, or actually I can look that for the first graph, I see that a lot of molecules have, or particles have, lower temperature or lower speed. That means they have lower temperature. And for the second graph, I can see that particles in average have higher average speed. So that means particles in the second one have higher temperature than particles in the first state. But now I have to connect this temperature to my graph. So I'm going to look at AB first. So when I look at AB, I can do PV over T is equal to PV over T. So I have PV, PA, VA over TA is equal to PB, VB over TB. Now, P is constant, so I don't have to keep my P here. So I can get rid of P. And VB is 1/4 of VA. So instead of VB, I can write 1/4 of VA. So VA and VA cancels. And that gives me that TA is equal to 4 times TB. So TA has higher temperature. TA has higher temperature than TB. then for BC, it's isothermal. So change of the temperature is equal to 0. So I cannot look at 1 and 2. So I cannot use for 1 and 2 my isothermal process because the temperature doesn't change for B to C. And then from C to A, I'm going to do the same. I have PC VC over TC is equal to PA VA TA. Because they have the same volume, I can get rid of the volume. And because the pressure of A is 4 times the pressure of C, so I can write here 4 times pressure of C. Then pressure of C can be cancelled. And it looks like your TA is equal to 4 times TC. So again, TA is bigger than TC. And that supports your claim because TA is equal to 4 times TB and 4 times TC, but TB and TC is the same temperature. Before I make my conclusion which state is which, so I rewrote them for you right here. I'm gonna look at the way the question is asked. They say curves 1 and 2 show the distribution of their particle speed when the sample of gas is in 2 states. Curve A occurs before curve 2. So for curve 1. So that means this curve occurs before the next one. And what we have here is higher temperature because TA is larger than TB and TC. So we have higher temperature, lower temperature, stays lower temperature, higher temperature. So in the only case where you have first lower temperature and then higher temperature, it's state C when you have lower temperature and then you have higher temperature. So your first one is is C, and your second one is A.